Full explanation of types of motor drivers in 5 minutes. Motor drivers are essential components in controlling the operation of motors by managing the direction, speed, and torque based on input signals. Here are some common types of motor drivers, each designed to control specific motor types. DC motor drivers control the operation of direct current DC motors by managing the voltage and current supplied to them. They are used in a wide range of applications, from small robotics to large industrial machines. Here are the main types of DC motor drivers. 1. H-bridge drivers. Function. H-bridge drivers are circuits that allow the control of the direction of current flow through the motor, enabling forward and reverse rotation. Operation. The H-bridge configuration has 4 switches, transistors or MOSFETs, arranged in an H shape. By turning these switches on and off in different combinations, the direction of the motor's rotation can be controlled. Applications. Widely used in robotics, automation, and applications where bidirectional control of DC motors is required. Examples: L298, L293D, and DRV8833 ICs. 2. PWM, Pulse Width Modulation Drivers. Function. PWM drivers control the speed of DC motors by adjusting the average voltage supplied to the motor. Operation. By rapidly switching the motor on and off at a certain frequency, duty cycle, PWM controls the average power. A higher duty cycle results in higher speed, while a lower duty cycle reduces speed. Applications. Useful in applications requiring variable speed control, such as drones, RC vehicles, and electric fans. Examples. PWM control is often integrated into other motor drivers like H-bridge ICs or MOSFET drivers. 3. MOSFET-based drivers. Function. MOSFET-based drivers are used to drive high-power DC motors where higher current handling is necessary. Operation. MOSFETs, metal oxide semiconductor field effect transistors, are used as switches that can control large currents with minimal heat loss, making them efficient for high-power applications. Applications. Common in high-power applications, such as electric vehicles, large industrial machinery, and robotics. Examples. High-power MOSFETs are often used along with microcontrollers or dedicated motor driver ICs to provide PWM control. 4. Current limiting drivers. Function. Protects the motor and circuit by limiting the current to a safe range. Operation. By incorporating current sensing circuits, these drivers monitor the current flowing through the motor. If it exceeds a set threshold, the driver limits or shuts off the power to protect both the motor and driver circuitry. Applications. Used in applications where sudden changes in load could cause current spikes, like in robotics or industrial machinery. 5. Full bridge and half bridge drivers. Full bridge drivers, similar to H-bridge drivers, but designed to handle higher power loads. These circuits can control both the speed and direction of the motor. Half bridge drivers. These control one direction of the motor and are useful in applications that only require one-way control or are used as components within full-bridge circuits. Applications. Full-bridge drivers are often used in bidirectional motor control applications, while half-bridge drivers are found in simpler circuits where unidirectional control is enough. 6. Integrated motor drivers with protection features. Function. These drivers have built-in protections such as over-temperature, over-current, and under-voltage lockout to enhance safety and reliability. Examples. ICs like TB6612FNG and L298 have integrated protections and control circuits to handle various loads safely. Applications. Widely used in consumer electronics and robotics where reliability and simplicity are important. Summary of key DC motor driver features. Direction control, enabled by H-bridge circuits for bidirectional movement. Speed control, achieved through PWM modulation. Power handling, MOSFETs and full-bridge designs handle higher power loads. Protection, integrated circuits offer protection against potential electrical faults. DC motor drivers are essential for a wide variety of applications, and choosing the right type depends on the motor specifications, required control features, and the application's demands. Stepper motor drivers are used to control stepper motors, which rotate in precise steps rather than continuously. These motors are commonly used in applications that require accurate positioning and speed control, such as 3D printers, CNC machines, robotics, and camera control systems. Here are the main types of stepper motor drivers. 1. Unipolar Stepper Motor Drivers. Function: Unipolar stepper motor drivers control motors with unipolar windings, where each winding has a center tap, allowing for simpler current control. Operation: These drivers energize the windings in a specific sequence to rotate the motor in discrete steps. Typically, only one half of the coil is energized at a time. Advantages: simpler design, often less costly, and lower power consumption since only half of the coil is energized at any given time. Disadvantages: provides lower torque compared to bipolar drivers. Applications: common in applications requiring less torque and lower precision. Examples: ULN 2003, L298. 2. Bipolar Stepper Motor Drivers. Function: Bipolar stepper motor drivers control motors with two-phase windings, where each phase is energized with alternating current to create a rotating magnetic field. Operation: Bipolar drivers reverse the current in the motor's windings to generate the magnetic field, allowing for a higher torque output. Advantages: higher torque than unipolar drivers, more efficient use of the motor windings. Disadvantages: requires more complex circuitry and can generate more heat due to the full use of the windings. Applications: common in high-torque applications, such as CNC machines, robotics, and 3D printers. Examples: A4988, DRV8825, TB6600. 3. Micro-stepping stepper motor drivers. Function: micro-stepping drivers control the stepper motor in very small increments of a full step, dividing the full step into smaller fractions, e.g., 1/2, 1/4, 1/8, or even 1/256 steps. Operation: by varying the current to each motor winding in smaller steps, the driver enables finer control over motor position, which results in smoother motion and quieter operation. Advantages: smoother, quieter motion with higher positional accuracy. Microstepping can reduce mechanical resonance and vibrations. Disadvantages: increased complexity in driver design and may require more current to maintain the same torque. Applications: used in precision systems, such as 3D printers, robotics, and CNC machines, where smooth motion and high resolution are critical. Examples: DRV8825, A4988, TMC2209. 3. Micro-stepping stepper motor drivers. Function: micro-stepping drivers control the stepper motor in very small increments of a full step, dividing the full step into smaller fractions, e.g., 1/2, 1/4, 1/8, or even 1/256 steps. Operation: by varying the current to each motor winding in smaller steps, the driver enables finer control over motor position, which results in smoother motion and quieter operation. Advantages: smoother, quieter motion with higher positional accuracy. Microstepping can reduce mechanical resonance and vibrations. Disadvantages: increased complexity in driver design and may require more current to maintain the same torque. Applications: used in precision systems, such as 3D printers, robotics, and CNC machines, where smooth motion and high resolution are critical. Examples: DRV8825, A4988, TMC2209. 4. Full step and half-step stepper motor drivers. Full step drivers. These drivers energize the windings fully in a stepwise fashion. In full step mode, the motor moves in large increments, one full step per pulse. Half-step drivers. These drivers alternate between energizing one winding or both windings, effectively doubling the resolution compared to full-step drivers. Operation: in half-step mode, the motor alternates between a full step and a half-step, providing smoother motion compared to full-step mode. Applications: full-step and half-step drivers are used in applications that don't require the fine resolution of micro-stepping, but where efficiency and basic control are more important. Examples: many basic stepper drivers, including the L298 full-step or the A4988 half-step. 5. Chopper stepper motor drivers. Function: these drivers regulate current to the stepper motor in a chopping manner, which helps to keep the current constant through each coil. Operation: the chopper refers to the driver's ability to turn the current on and off rapidly using PWM to maintain a constant current through the motor windings, ensuring efficient operation and reducing overheating. Advantages: efficient current control, prevents motor overheating, and improves overall performance. Applications: used in applications requiring high efficiency and smooth control, such as in robotics, 3D printing, and CNC machines. Examples: DRV8825, TB6600. 6. Closed-loop stepper motor drivers, servo-based. Function: closed-loop stepper drivers combine the features of stepper motors and servos by using feedback mechanisms, such as encoders, to adjust the motor's position and speed in real time. Operation: these drivers use sensors to monitor the motor's position and speed, making adjustments as needed to avoid missing steps, improving efficiency and reducing heat generation. Advantages: more efficient and precise than traditional stepper drivers. Reduced heat generation and lower power consumption. Higher torque at higher speeds. Applications: typically used in applications where performance is critical, such as in robotics, automation, and high-performance CNC machines. Examples: Leadshine AM882, ClearPath servos. Summary of key stepper motor driver features. Current control: stepper drivers manage the current through the motor windings, which determines torque and stability. Step control: the motor's movement is controlled by the number of steps or pulses sent to the driver, with microstepping offering fine resolution. Modes of operation: full step, half step, and microstepping offer different performance trade-offs in terms of smoothness, torque, and speed. Heat management: many drivers include features like chopper circuits or current limiting to prevent overheating and improve motor performance. Position feedback: closed-loop systems incorporate feedback to improve motor efficiency and reliability. Applications of stepper motor drivers. Robotics: for precise movement and control in robotic arms and mobile robots. 3D printers: to control the movement of print heads and beds. CNC machines: for controlling the motors that drive the cutting tools and machine parts. Camera systems: used in gimbals or lens focusing systems where precise positioning is critical. Medical equipment: for devices requiring precise motion control, such as in pumps or actuators. Stepper motor drivers are crucial components in systems requiring high precision and control over motor movement, and the type of driver used depends on the specific needs of the application, such as torque, speed, and smoothness of motion. Servo motor drivers are used to control servo motors, which are typically employed for precise control of angular position, velocity, and acceleration. Servo motors are widely used in applications requiring high precision, such as in robotics, automation, camera systems, and control systems. Unlike stepper motors, servo motors provide continuous rotation with feedback control, which makes them ideal for applications where accurate positioning is needed. Here's an overview of servo motor drivers. 1. Basic servo motor drivers, PWM-based. Function: basic servo drivers control the rotation of the motor by generating a PWM, pulse width modulation, signal. This signal determines the position of the servo shaft. Operation: servo motors typically have a control input that requires a PWM signal with a fixed frequency, e.g., 50 Hz. The position of the motor shaft is determined by the duty cycle of the PWM signal. A pulse width of 1.5 milliseconds corresponds to the neutral position, e.g., 0 degrees. Pulse widths longer or shorter than 1.5 milliseconds cause the motor to rotate in one direction or the other, typically 0 to 180 degrees. Applications: used in simple control applications where precise angular positioning is needed, such as in model airplanes, robotic arms, and camera gimbals. Examples: SG90, MG995, and standard servo motors controlled by PWM signals from microcontrollers like Arduino. 2. Digital servo drivers. Function: digital servo drivers provide more advanced control features than basic PWM drivers. They offer higher resolution, better response times, and more advanced feedback mechanisms. Operation: these drivers often integrate digital signal processing, DSP, and microcontrollers to enhance performance. They provide finer resolution and smoother control over the motor's movement and may include built-in safety features like over-temperature protection and current limiting. Advantages: higher precision and faster response times. These drivers are typically used in applications requiring high performance and reliability. Applications: common in high-precision robotics, CNC machines, and professional camera equipment. Examples: Dynamics LAX-12, RoboClaw, motor controllers with digital control. 3. Closed-loop servo drivers, feedback-based. Function: closed-loop servo drivers combine feedback mechanisms, usually encoders or resolvers, with the motor's control system to continuously monitor the motor's position and make adjustments in real time. Operation: these drivers ensure that the motor maintains its position, speed, and torque even under varying load conditions. Feedback from the encoder is used to detect discrepancies between the commanded position and the actual position, allowing the system to correct itself. Advantages: higher accuracy, better torque performance at high speeds, and the ability to maintain precise positioning even in dynamic environments. These drivers also help prevent stalling and overshooting, which can occur in open-loop systems. Applications: used in high-performance robotics, industrial automation, CNC machines, and applications requiring real-time adjustment to changes in load. Examples: Kollmorgen, Mitsubishi, and other industrial-grade servo systems with feedback control. 4. AC servo motor drivers. Function: AC servo drivers control AC servo motors, which are typically used in industrial applications. These drivers control the motor's speed, torque, and position by regulating the input power. Operation: AC servo drivers often use vector control or field-oriented control (FOC) to precisely control the motor's torque and speed by adjusting the frequency and amplitude of the AC power supplied to the motor. Advantages: AC servos offer higher torque density, smooth operation, and efficient performance, particularly in applications requiring continuous rotation and high torque. Applications: industrial automation, robotics, CNC machines, packaging machinery, and more. Examples: Mitsubishi Mel Servo, Yaskawa Sigma 7. 5. Brushless DC, BLDC, servo drivers. Function: BLDC servo drivers control brushless DC motors used in servo applications. These drivers control the motor using feedback from Hall sensors or encoders to ensure accurate position and speed control. Operation: BLDC servo drivers use a 3-phase inverter to supply the motor with controlled power. The feedback loop continuously adjusts the motor's rotation, ensuring smooth operation and minimizing loss. Advantages: BLDC motors are more efficient than traditional brushed motors and require less maintenance due to the absence of brushes. They are also quieter and can provide higher torque and speed at smaller sizes. Applications: used in robotics, drones, and electric vehicles, as well as in applications requiring high efficiency and precision. Examples: VSC, open source controller for BLDC motors, ODrive, and Trina Mic. 6. Integrated servo motor and driver systems. Function: in some applications, the servo motor and driver are combined into a single unit, reducing the complexity of installation and wiring. Operation: these integrated systems include both the motor and the driver in one package, making them easier to set up and configure, especially in compact systems. Advantages: simplifies wiring and installation. These systems often come pre-calibrated and may include diagnostic tools and safety features, making them ideal for space-constrained applications. Applications: used in automated machines, robotic arms, and other applications where space is limited and ease of installation is essential. Examples: Lead Shine integrated servo motors, iDrive by Intelligent Motion Systems. 7. Servo motor drivers with programmable control. Function: these servo drivers include programmable logic that allows users to define motion profiles, torque limits, acceleration, deceleration, and other parameters. Operation: the driver typically includes an embedded microcontroller or FPGA that executes a predefined set of commands or algorithms, allowing the motor to follow a specific motion pattern. The control is usually programmable via a graphical interface or communication protocol, e.g., Modbus, CA-NOPN. Advantages: highly flexible and customizable for various industrial applications. They provide precise motion control and can execute complex motion profiles, such as trapezoidal or sinusoidal trajectories. Applications: used in automated manufacturing, packaging, material handling, and robotic systems where customizable motion sequences are required. Examples: Beckhoff servo drives, Omron servos. Summary of key features. PWM control, the basic form of control, where the motor's position is determined by varying the pulse width. Feedback control. Closed-loop systems provide real-time position and speed feedback for high accuracy and stability. Motor type. Servo drivers can be designed for different types of motors, including AC, BLDC, and DC motors. Programmability. Some drivers allow users to program motion profiles, speeds, and other parameters for more customized behavior. Integration. Integrated servo systems combine the motor and driver into a single unit for ease of use and compact design. Applications of servo motor drivers. Robotics. For precise movement control in robotic arms, actuators, and drones. Industrial automation. To control machines and equipment such as conveyors, packaging machines, and CNC tools. CNC machines. To control the axes and spindles of milling, lathe, and cutting machines. Camera systems. Used in gimbals and autofocus mechanisms to precisely control the camera's orientation. Electric vehicles. In control systems for electric motors in cars, bikes, and drones. Servo motor drivers are essential for any application requiring precise, reliable, and efficient motion control. The type of servo motor driver chosen depends on the motor type, application requirements, and the desired level of precision. Brushless DC, BLDC, motor drivers are used to control BLDC motors, which are commonly found in applications requiring high efficiency, durability, and low maintenance. Unlike brushed DC motors, BLDC motors have no brushes, which eliminates the need for mechanical contact between the rotor and stator, providing smoother operation, greater efficiency, and longer lifespan. Here's an overview of BLDC motor drivers. 1. Basic BLDC motor drivers. Function. Basic BLDC motor drivers provide the essential functionality to drive a BLDC motor, typically using a 6-step commutation process, which involves controlling 3 phases of the motor in a specific sequence. Operation. These drivers switch the power supply to the motor's windings using MOSFETs or IGBTs. The driver uses a predefined sequence, usually 120 degrees apart, to energize the windings, which generates a rotating magnetic field that causes the rotor to spin. Control method. Basic drivers generally require an external controller, such as a microcontroller or a PWM signal generator, to provide the necessary commutation signals. Applications. These are commonly used in applications that don't require sophisticated control, like in simple fan systems, some types of power tools, or hobbyist projects. Examples: L298, DRV8871, TB6612. 2. BLDC motor drivers with Hall sensor feedback. Function. These drivers include Hall sensors, or encoders, for feedback to determine the rotor position. The Hall sensors provide real-time data about the motor's position, which allows the driver to commutate the motor correctly and ensure smooth operation. Operation. The driver uses feedback from the Hall sensors to determine the position of the rotor and select the appropriate phase of the motor to energize. This results in more accurate and efficient commutation, especially at low speeds or under load. Advantages. Hall sensor feedback helps to ensure that the motor runs smoothly without stalling or cogging, particularly in low-speed operation. It also improves torque control and allows for smoother starts and stops. Applications. Commonly used in applications where the motor must operate at low speeds, such as in robotics, drones, electric vehicles, and high-precision tools. Examples: VSC, DRV8301, STSPIN. 3. Sensorless BLDC motor drivers. Function. Sensorless BLDC motor drivers do not use Hall sensors or encoders to detect rotor position. Instead, they rely on the back electromotive force, back EMF, generated by the motor to determine the rotor's position. Operation. Sensorless drivers estimate the rotor position based on the voltage generated by the spinning rotor, back EMF. These drivers are typically used when lower-cost solutions are required, as they do not need extra sensors. The rotor position is inferred indirectly from the motor's electrical properties. Advantages: no need for physical sensors, leading to lower system complexity and cost. These drivers are more robust and suitable for applications where the rotor's position is not required to be highly precise. Disadvantages: sensorless drivers can struggle with low-speed operation or during startup because the back EMF is too small at those points to provide reliable feedback. They are generally not as efficient as sensor-based systems at low speeds. Applications: used in higher speed applications or in systems that do not require precise low-speed control, such as electric scooters, fans, and high-performance power tools. Examples: O-Drive, sensorless configuration, DRV8312, and custom sensorless controllers for hobbyist use. 4. BLDC motor drivers with field-oriented control, FOC. Function: FOC is a more advanced control technique used in BLDC motor drivers that allows precise control over the motor's speed, torque, and position. FOC drives the motor based on the vector control method, aligning the current vector with the rotor magnetic field for optimal efficiency. Operation: FOC involves complex algorithms that dynamically adjust the motor's stator current to align with the rotor's magnetic field, providing smooth, continuous motion. FOC can be applied with both Hall sensors and sensorless configurations. Advantages: FOC provides superior efficiency, smoother operation, and more precise control over torque and speed compared to simple 6-step commutation. It also reduces noise and vibration and improves the motor's performance at low speeds. Disadvantages: more computationally intensive and requires advanced algorithms and processing power. It also increases the cost and complexity of the driver. Applications: common in high-performance systems where smooth control is essential, such as in electric vehicles, EVs, drones, robotics, industrial automation, and other precision motion control systems. Examples: VSC, for electric skateboards and drones, O-Drive, for robotics and electric vehicles, ST Microelectronics Spin Series. 5. Integrated BLDC motor drivers, Motor Plus Driver. Function: these are integrated systems where the BLDC motor and the driver circuit are combined into a single unit. This simplifies installation and wiring for compact systems. Operation: the driver module and motor are often designed to work together, making them easier to configure and control. These integrated solutions may include sensors, such as Hall sensors or encoders, as well as additional features like thermal protection or current sensing. Advantages: easier to implement and compact. These systems are ideal for applications where space is limited and ease of installation is a priority. Applications: used in robotics, drones, appliances, and small machines where space, simplicity, and integration are important. Examples: Maxon ECI40, integrated BLDC motor and driver, Nidec BLDC motor systems. 6. Digital BLDC motor drivers. Function: digital BLDC motor drivers use a digital signal processing, DSP, or microcontroller-based control system to precisely manage the motor's operation. Operation: these drivers process inputs from sensors or use sensorless methods and generate control signals for commutation. The digital control allows for more sophisticated features, such as programmable motor profiles, speed control, fault detection, and real-time adjustments. Advantages: digital drivers can offer enhanced flexibility, programmability, and integration with advanced control techniques like FOC. They can also implement features such as overcurrent protection, speed regulation, and error detection. Applications: used in advanced systems where flexibility, programmability, and high-performance motor control are required, such as in robotics, automated machinery, and electric vehicles. Examples: VSC, O-Drive, ST Microelectronics Spin. 7. High-power BLDC motor drivers. Function: these drivers are designed to handle higher currents and voltages, making them suitable for high-power applications. Operation: these drivers can control large BLDC motors typically found in electric vehicles, EVs, industrial machinery, and high-performance robotics. They use sophisticated algorithms, such as field-oriented control, FOC, to efficiently manage high-power motors. Advantages: high power output and robust performance for demanding applications. Often used in combination with cooling systems and advanced protection features. Applications: electric vehicles, industrial robots, high-speed machinery, and large-scale automated systems. Examples: Tesla motor controller, VSC, 4 high-power electric skateboards and vehicles, O-Drive for high-performance robotics. Summary of key features. Commutation methods. BLDC motor drivers use different methods of commutation, including 6-step and sinusoidal commutation. Sensor-based or sensorless control may be used. Feedback control. Drivers can use Hall sensors, encoders, or back EMF for rotor position feedback, or operate sensorless, using just the motor's electrical characteristics. Control techniques. Advanced techniques like field-oriented control, FOC, provide smoother, quieter operation and higher efficiency compared to traditional commutation methods. Integration. Integrated solutions that combine the motor and driver simplify system design, especially for compact applications. Power handling. BLDC drivers range from low-power solutions for hobbyist applications to high-power drivers for electric vehicles and industrial machinery. Applications of BLDC motor drivers. Electric vehicles, EVs, for driving the wheels or actuators with high efficiency and precision. Robotics, used in robotic arms, legs, drones, and other autonomous systems. Industrial machinery, for controlling conveyors, pumps, actuators, and CNC machines. Drones, to control the rotors in multi-rotor drones, quadcopters, hexacopters. Cooling systems, used in computer fans, HVAC systems, and automotive fans. Power tools, for driving motors in tools like drills, saws, and other electric tools. BLDC motor drivers are essential for applications that require high efficiency, low maintenance, and long motor life. The choice of driver depends on the complexity of the motor control, power requirements, and the type of feedback, sensor-based or sensorless, needed for precise operation. AC motor drivers, specifically variable frequency drives, VFDs, are used to control the speed, torque, and direction of AC motors, both induction motors and synchronous motors. A VFD works by adjusting the frequency of the power supply to the motor, allowing for precise control over its performance, efficiency, and speed. VFDs are commonly used in industrial, commercial, and residential applications where motor speed needs to be varied based on load, demand, or operational conditions. One function of AC motor drivers, VFDs. Speed control. By varying the frequency of the AC power supplied to the motor, VFDs can control the motor's speed. The motor's speed is directly proportional to the frequency of the input signal. This allows for efficient speed regulation, which is crucial in processes requiring variable speeds. Torque control. VFDs can also control the motor's torque by adjusting the voltage applied to the motor along with the frequency. This allows for smoother starts, stops, and load handling. Energy efficiency. VFDs can significantly improve energy efficiency by adjusting motor speed to match the load requirement, reducing power consumption compared to running motors at full speed constantly. 2. Basic operation of VFDs. VFDs typically consist of 3 main components. Rectifier converts AC power from the power supply into DC. DC bus smoothens the DC signal to maintain a stable voltage. Inverter converts the DC back to AC with a variable frequency and voltage to drive the motor. The VFD adjusts the frequency of the output AC by controlling the inverter, which determines the motor's speed and torque. 3 types of AC motor drivers, VFDs. A volts per hertz, V/F control. Function. V/F control is a basic method of controlling AC motor speed in VFDs. The voltage is adjusted in proportion to the frequency to maintain a constant ratio, which ensures that the motor operates within safe limits. Operation. As the frequency increases, the voltage is also increased to maintain the magnetic field strength in the motor. This simple method is typically used for applications where precision and speed control are not critical. Advantages: simple to implement and cost-effective for basic applications. Applications: fans, pumps, conveyors, and other systems requiring basic motor control. Examples: basic VFDs for HVAC systems, general-purpose industrial fans. B. Vector control, field-oriented control. Function: vector control, also known as field-oriented control or FOC, offers more advanced control by precisely managing the current flow in the motor's windings to control both torque and speed. It involves splitting the motor's stator current into 2 components, one for controlling the torque and the other for controlling the flux. Operation. The vector control method allows independent control of the torque and the flux, which provides more precise speed control and better dynamic performance compared to V/F control. Advantages. Offers higher efficiency, better performance, faster response time, and smoother motor control. It is ideal for applications requiring precise motor control under varying loads. Applications. CNC machines, robotics, elevators, high-performance fans, and pumps. Examples. Premium VFDs from manufacturers like Siemens, Dynamics, ABB, ACS Series, and Schneider Electric, Altivar. C. Direct Torque Control, DTC. Function. DTC is a more advanced control method compared to vector control. It directly controls the motor's torque and flux without requiring the intermediate step of current regulation. Operation. DTC uses real-time feedback from the motor to adjust the torque and flux. This results in faster torque response and more accurate motor control. DTC is typically more sophisticated and provides a smoother, more responsive performance. Advantages. Faster response, high precision, and better control under high dynamic loads. It also reduces the need for speed sensors, making the system more robust. Applications. High-performance applications where precise control and rapid acceleration/deceleration are needed, such as in robotics, electric vehicles, EVs, and high-speed machinery. Examples. High-end VFDs from manufacturers like Siemens, Dynamics S120, ABB, ACS 880. 4. Key features of VFDs. Speed control. The primary function of VFDs is controlling the speed of the motor. Speed can be adjusted smoothly from 0 to the motor's rated speed, allowing for more efficient operation and flexibility. Torque control. Some VFDs can precisely control the motor's torque, making them suitable for applications where torque stability is critical. Soft start/stop. VFDs provide a smooth ramp-up and ramp-down of motor speed, preventing mechanical shock, reducing wear, and preventing excessive current draw during startup. Energy savings. By adjusting motor speed to match the load, VFDs help reduce energy consumption, particularly in applications where full-speed operation is not always necessary. Overload protection. VFDs include protections for overcurrent, overvoltage, and thermal overloads to prevent damage to the motor and drive. Regenerative braking. Some VFDs can convert the motor's kinetic energy into electrical energy, which is fed back into the power supply, reducing energy consumption and providing braking capability. Communication interfaces. Many modern VFDs support communication protocols such as Modbus, Profibus, Ethernet/IP, and CAN-Open, which enables remote monitoring, control, and integration into automation systems. 5. Applications of VFDs. Pumps. VFDs allow for variable control of pump speeds, which is useful in applications such as water treatment, oil and gas, and HVAC systems. Fans. In systems like ventilation and air conditioning, VFDs help control fan speed to optimize airflow, reduce energy consumption, and maintain consistent performance. Conveyors. VFDs enable the control of conveyor belt speeds in manufacturing and material handling systems, improving throughput and operational efficiency. Elevators. VFDs are used to control the speed and smooth acceleration of elevators, providing a comfortable ride and reducing energy usage. CNC machines. In industrial manufacturing, VFDs allow precise control over the spindle speed and feed rates, enabling high-precision machining. HVAC systems. VFDs are commonly used in air handling units, AHUs, and chillers to control fan and pump speeds, optimizing energy efficiency and improving performance. Electric vehicles. VFDs are used to control the speed of the electric motor, optimizing acceleration and deceleration performance. 6. Advantages of using VFDs. Improved energy efficiency. VFDs reduce energy consumption by adjusting the motor speed to meet the exact needs of the load. Reduced wear and tear. By controlling acceleration and deceleration rates, VFDs help to extend the life of motors and mechanical components. Enhanced process control. VFDs provide precise control of motor speed, allowing processes to operate at their optimal conditions. Reduced noise and vibration. Smooth acceleration and deceleration help minimize motor noise and mechanical vibrations. Cost savings. Although the initial cost of VFDs can be higher, they provide long-term cost savings due to energy efficiency and reduced maintenance costs. Flexible operation. VFDs offer a range of control options, from simple speed regulation to advanced torque and position control, making them adaptable to a wide variety of applications. 7. Types of AC motors controlled by VFDs. Induction motors, the most common type of AC motor controlled by VFDs. They are rugged, reliable, and suitable for most general-purpose applications. Synchronous motors, used in applications requiring constant speed and high precision. VFDs can be used for controlling these motors as well, though they are typically more expensive and require more complex control systems. Permanent magnet synchronous motors, PMSMs, often used in applications requiring high efficiency and low maintenance, such as in electric vehicles and robotics. Conclusion. Variable frequency drives, VFDs, are an essential component in modern motor control systems. By adjusting the frequency and voltage supplied to the motor, VFDs offer precise speed and torque control, improve energy efficiency, and extend the life of both the motor and mechanical components. They are used across a wide range of industries and applications, including HVAC, industrial automation, electric vehicles, and robotics. The choice of control method, whether V/F, vector control, or direct torque control, depends on the specific requirements for performance, efficiency, and precision in the given application. Universal motor drivers are used to control universal motors, which are a type of electric motor that can run on both AC and DC power sources. Universal motors are widely used in applications requiring high starting torque and variable speed control, such as in household appliances, power tools, and small appliances. Unlike AC induction motors, universal motors have a field winding on the stator and an armature winding on the rotor, which allows them to operate on either DC or AC power. 1. Function of universal motor drivers. Universal motor drivers are designed to control the speed, direction, and operation of universal motors. They typically handle the following tasks. Speed control. Universal motors have a linear relationship between the applied voltage and speed. By varying the input voltage or pulse width modulation, PWM, signals, the driver can adjust the motor's speed. Direction control. By reversing the polarity of the DC voltage applied to the motor, the direction of rotation can be changed. Overcurrent protection. The driver protects the motor by sensing excessive current and shutting down the motor if necessary to prevent damage. Soft start/stop. Drivers can provide a smooth start and stop to reduce mechanical shock and prevent damage to the motor and connected load. 2. Basic operation of universal motor drivers. Universal motors typically operate by applying a voltage to both the field winding on the stator and the armature on the rotor. The driver modulates this voltage to control motor operation. There are two main approaches used to control the motor. AC voltage control. In AC applications, the motor driver controls the voltage applied to the motor by adjusting the power supply. It typically uses a triac-based phase control or thyristor to adjust the power waveform fed to the motor. This is often done through phase-cutting methods, such as zero-crossing switching. In this mode, the motor speed is proportional to the voltage applied, but control can be somewhat less efficient compared to DC control. DC voltage control. In DC mode, the universal motor behaves like a standard DC motor, where the driver adjusts the DC voltage to control the speed of the motor. This is often achieved using pulse width modulation, PWM. By varying the duty cycle of the PWM signal, the average voltage applied to the motor is adjusted, which in turn controls the motor speed. 3. Speed control methods. Voltage control, the simplest method for controlling a universal motor. By adjusting the voltage applied to the motor, the speed is varied. This can be done using either a variable resistor or a PWM controller. Pulse width modulation, PWM. In this method, the motor driver uses a PWM signal to control the average voltage applied to the motor. The motor speed is adjusted by changing the duty cycle of the PWM signal. The percentage of time the signal is high versus low. The higher the duty cycle, the more power is delivered to the motor, increasing its speed. A lower duty cycle reduces the average voltage, slowing the motor down. Phase control, AC applications. In AC applications, Phase control techniques such as triac-based dimmer circuits or thyristor-controlled systems can control the motor's speed by adjusting when the AC voltage is applied to the motor. 4. Common universal motor driver components. Universal motor drivers are often built using the following components. Triac/thyristor, used in AC applications for controlling the power fed to the motor. MOSFETs, commonly used in DC motor drivers and for switching the voltage in a PWM-controlled system. PWM controller, a key component for adjusting the average voltage in a DC motor drive. Operational amplifiers, used in feedback control systems to regulate speed or current. Current sensing circuit, to detect overcurrent situations and provide protection. 5. Types of universal motor drivers. Universal motor drivers can vary in complexity based on the features they offer and the type of motor control required. Some of the common types include A. Basic universal motor drivers. These drivers provide basic speed and direction control, typically using simple voltage control or low-complexity PWM circuits. Features: simple speed adjustment, forward/reverse direction control, basic overcurrent protection. Applications: small household appliances like mixers, vacuum cleaners, or portable fans. Examples: low-cost motor drivers used in small power tools and home appliances. B. Advanced universal motor drivers with feedback control. These drivers offer more advanced features such as precise speed control and feedback mechanisms for better torque and performance regulation. Features: precise speed control, torque regulation, overcurrent and overvoltage protection, thermal shutdown, and more efficient operation. Applications: power tools, industrial machinery, and more demanding consumer appliances. Examples: drivers used in industrial-grade equipment, power tool controllers, and high-performance appliances. 6. Applications of universal motor drivers. Universal motor drivers are found in many consumer and industrial products where a compact, high-torque motor is required, and they are typically used in power tools, drills, saws, grinders, and other hand tools. Household appliances, vacuum cleaners, mixers, blenders, food processors, and washing machines. Industrial machines, small conveyor systems, winches, and sewing machines. HVAC systems, fans and blowers and air conditioning systems. Electric toys, for high-speed motors in toy cars, trains, or other battery-powered devices. 7. Advantages of universal motor drivers. High starting torque. Universal motors offer high torque at startup, which makes them ideal for power-hungry applications like drills and vacuum cleaners. Compact size. Universal motors are typically more compact compared to other motor types, which is advantageous in consumer appliances where space is a premium. Versatility. These motors can operate on both AC and DC power, making them versatile for different types of equipment. Cost-effective. Compared to more sophisticated motor types like BLDC or AC induction motors, universal motors and their drivers tend to be less expensive, making them ideal for budget-sensitive applications. Simple control. Speed control through voltage or PWM is relatively simple to implement, making universal motor drivers popular in a wide range of consumer devices. 8. Disadvantages of universal motor drivers. Limited efficiency. Universal motors are less efficient compared to other motor types like induction or brushless DC motors. This can lead to greater energy consumption and heat generation. Brush wear. Since universal motors are brush-type motors, the brushes wear out over time, leading to maintenance needs. Noise. Universal motors can be noisier than other motor types, which can be a concern in noise-sensitive applications. Limited speed range. While universal motors can be controlled for speed, they are typically not as precise as BLDC motors or AC motors in certain applications. 9. Conclusion. Universal motor drivers are essential for controlling universal motors, which are widely used in applications where high-speed operation, compact size, and simplicity are key requirements. These drivers use methods like voltage control and PWM to manage motor speed, torque, and direction. They are cost-effective, efficient for high-torque tasks, and are typically used in household appliances, power tools, and industrial machinery. However, they are less efficient and can require more maintenance than other motor types, such as brushless DC or AC motors. Each type of motor driver serves unique purposes and applications, varying in complexity, cost, and power requirements based on the motor and application specifics.